The Sega Genesis was released in North America on August 14, 1989, and it took the world by storm. Also known as the Sega Mega Drive in Japan, this video game console, over its lifetime, sold about 30.75 million units, and created some really classic games that still have a cult following today. Between the Super Nintendo and the Sega Genesis, this initiated market competition to fight for sales and assert dominance in the market. This was what was known as the console war, and this console war drove innovation for the next 15 years in terms of what was possible from a video game console. And although Sega really struck out with its successor, the Sega Saturn, the Sega Genesis was a huge success, partly due to its simple architecture and its straightforward nature. Game studios and developers clearly loved the Genesis, as its library of games spans 713 across all regions of the world. So not only did it not make a name for itself as a difficult console to develop for, but it produced a lot of profitable and fun games on it, and that is a one heck of an achievement in my eyes, and it primarily has to do with the hardware architecture that set the platform up for development for developers to make these great games. And that is what we're going to be talking about today. Hi everybody, I'm James from Zygal Studios, and today we're talking about the hardware architecture of the Sega Genesis. You couldn't mention video game console without the words Zilog or Motorola, usually in this time period, and the Sega Genesis is no exception. It has two general-purpose CPUs, the Zilog Z80, which was very common, used after and before this system, to do sound processing, and the 68000 to do general-purpose computing. This was kind of unusual at the time, and Sega was worried that the 68K wouldn't be able to handle the complex video display processing as well as the sound processing, so the Zilog Z80 was actually thrown on there in order to specifically handle tasks related to audio. The Motorola 68K was clocked around 7.59 MHz and had the famous 68K instruction set. This instruction set was paired with a set of 32-bit registers, but what's odd was that the ALU and the data bus were only 16 bits long, so this means that in order to get things from the registers to these pieces, you had to do two sequential writes on the bus in order for the ALU to operate on them completely, and then two sequential writes back to the register in order to get the full 32-bit value to actually be placed and moved and operated on. This was paired with a 24-bit address bus that connected the 68K to the rest of the different processors and peripherals on the board. These concluded of some RAM, which is about 64 kilobytes, the Zilog Z80 to do the audio processing or other miscellaneous tasks, and this was actually controlled by a bus arbiter. A bus arbiter is a separate component in between a network of serial communication that deals with a multi-master system, meaning that there are multiple different peripherals on this communication network that can talk at any given time. The arbiter's job is to tell which piece of the system can actively communicate at a time, because as you can imagine, if multiple masters try and talk on the bus at the same time, you'll run into collisions on the bus, or hazards of which the bus can actually become totally unreadable. There are really two types of arbiters, but we can get that into a later video. The point is that the Genesis had a bus arbiter to help communicate with the Zilog Z80 and with the 68K. There were some expansion ports, some motherboard registers, and the video controllers, as well as some I/O and DMA, and of course your controller ports. What an odd pairing though, right? 32-bit registers from a 24-bit bus into a 16-bit ALU through a 16-bit data bus? Sounds kind of crazy, but it actually worked okay. The Zilog Z80 had the Z80 instruction set. It had a 16-bit address bus instead of the 24 that you saw in the 68K, and this was connected to 8 kilobytes of RAM, as well as a few sound chips, and the 68K's RAM to actually double buffer. What's bizarre is that this processor only had a 4-bit arithmetic logic unit, but it could handle 8-bit operations because it was quick. So the two writes that we were talking about before, like you saw on the 68K from the register to the ALU that happened in succession, had a similar principle here, and the Z80 was actually able to compute things quick enough to the point where two operations were roughly the same as one 8-bit operation. The system ran at about 3.49 MHz. Now let's talk about the video processing. So one of the biggest takeaways from advertising of this era in terms of video game consoles is that Sega Genesis had blast processing and the Super Nintendo doesn't, right? So what is blast processing? Well, truth be told, in my research, I really couldn't find a definitive answer for that. And really, what it eventually boiled down to was there really was no official technical explanation of what blast processing was. In fact, it was a marketing term that was coined by Sega of America to try and separate the consoles from each other, being the Super Nintendo and the Genesis. Now, in terms of blast, the closest thing I can think of is in terms of DMA controlling. So if we're talking about a DMA, sometimes in embedded systems you have what's called burst controlling, and burst controlling can be used in a number of applications, basically shoving different waveforms using the DMA across the line electrically, whether it's different frequency or different amplitude, can be controlled using the DMA as a burst controller to either save power or activate certain peripherals inside of a network. That's the closest thing I can get to, but blast and burst aren't necessarily the same thing. So blast processing probably referred to the fact that the Sega Genesis had a little bit more of a clock speed advantage versus the Super Nintendo. The graphics data was processed by the 68K but rendered on a video display processor. This video display processor ran around 13 MHz and had a couple modes of operations. Mode 4 basically was treated like the master system. Mode 5 is what the default mode of the system was in order to process the next generation graphics. The video display processor was controlled via a DMA from the 68000. The DMA was connected to the 64 kilobytes of RAM that we saw connected to the 68K. But the video display processor also had an 8-bit bus that communicated with 64 kilobytes of video RAM, and this was used to buffer for the 80-byte VS RAM, as well as some more static RAM that was available in 128 bytes. So, as you can see, the RAM inside the video display processor was pretty light. The color RAM, or the CRAM, which is 128 bytes, stored 4 color palettes. Each had 16 colors, and the system had 512 colors to choose from. The vertical scroll RAM, or the VS RAM, was essentially used to support horizontal and vertical scrolling. These scroll values would be stored in a different place, like for example in the video RAM, and then transferred over that 8-bit bus to the VS RAM. In terms of the way the graphics were laid out programmatically, the video display processor wasn't all that much different than the Super Nintendo's. It uses 8x8 bitmaps, in this case we call them tiles, to compose planes, and these planes would eventually fill up the screen. Each of these 8x8 bitmaps were encoded in a 4-byte array, where each entry corresponds to a pixel and the value associated with that. The game ROM actually held these tiles inside of the ROM and were transferred into the VRAM so the VDP could actually process them. But due to the bus arbiter and the DMA, there were only specific time windows where video data could actually come into the VRAM and be processed from the CPU. This would be quite a challenge in terms of the CPU control, but thanks to the DMA, it makes this process much easier. We can get into more what a DMA is specifically in a later video. DMA is direct memory access for short. And a direct memory access peripheral essentially takes one piece of data and moves it from one area in the memory architecture to another. This lets the CPU do other things while this peripheral is simply moving pieces of memory from one address to another. So while the CPU could process all the crazy graphics stuff, the DMA could take the stuff from video RAM and store it into the video display processor without the CPU actually having to do anything. So while the Z80 was used for specific audio processing, it also had standalone processing chips such as the Yamaha YM2612 and the Texas Instruments SN76489. As most games at this time, it used PCM samples at 8-bit resolution at 32K sampling, and it uses frequency modulation in order to synthesize the waveforms. The Z80 was in charge of controlling these two chips, and eventually was able to send that data actually to the physical audio hardware. Now, you're probably wondering, what was it actually like to develop on? Well, as many games of this time, pretty much all, were all developed in proprietary assembly, and in this case, the instruction sets you're working with are the 68K instruction set, as well as the Z80 instruction set. And the 68K instruction set was very familiar at the time, specifically being in both Apple computers and other video game consoles later on. And the Z80, the same thing. It's been used in multiple game consoles, past and present. But typically, the code would reside in the ROM, but the Z80 would have to have the sound driver code in order to actually operate the audio and be told what to do, whereas the ROM would store the information of how to control the Z80. So you would have to write code for the Z80 specifically to actually do the audio sampling, but you would also have to write 68,000 assembly in order to tell the Z80 what to do, and also do all the video processing as well as the main game logic. So you were writing a lot of assembly code in order to control the game itself and how it was rendered, and also how the sound was played. Sounds like a complicated dance, but for the time it actually was pretty straightforward, and thus ROMs were smaller and games were easier to be made, which is why there were so many that were made for the system and why the system was so successful. I hope you enjoyed this overview of the Sega Genesis hardware architecture and a little bit about what it was like to develop for. If you liked the video, please drop me a thumbs up and subscribe to me, as it helps me a lot. And if there's anything I missed or anything you want me to talk about in the future, please leave it in the comments below. I hope you all have a newfound appreciation for the Sega Genesis, and I hope to see you in the next video. This is James from Zygal Studios, signing off.